Okay, like to talk to you from the perspective of someone who finds a lot of these models extremely complicated in terms of high resolution X-ray spectroscopy. Um, a lot of the things we've been talking about, there really is not a lot of expertise out there in the general community, and I think the overall message I like to get here is high resolution X-ray spectroscopy is extremely hard. The optical folks really don't know how easy they have it in comparison to us. And the expertise out there in the wider community, especially as it's applied to developing uh, models for the community as a whole to use is somewhat rare. And this was, I think, a very serious comment that Chris Reynolds made in his farewell speech as when he was leaving the chair of head, that we should have as a society, a ban of Randall Smith, Gail Castor, and Tim Kalman from ever sharing the same mode of transportation at the same time. If anything ever happened to them, we would be in trouble. So I come from the perspective of someone with not really nearly that much expertise, trying to think of ways of trying to make things easier for us and understand how we can go about looking at these complex models in these very complex set of spectra. And one of the things I note is that we tend to make it a lot harder on ourselves in a lot of ways. And one of those ways is that we always tend to push towards the very limits of signal to noise. Now, part of that is inevitable because of the fact that our X-ray detectors are only so big. And when you're looking at high resolution spectroscopy, by definition, it really does mean there are lots and lots of bins that we have to fill. So we've got this kind of crazy combination in our field of these detectors with a lot of bins that we have to fill, plus very slow working and very complex models. And that can cause some heartache and pain when trying to get people to jump into this field and do work on it. Now, of course, one of the issues is that we really do need much larger effective area emissions. Thankfully, for the high energy part of high resolution X-ray spectroscopy, we will have CRISM in 3 or 4 years, and that is going to be great for things above 1 kV. That's still going to leave a gap for a high effective area, high spectral resolution instrument for below 1 kV. And to give a plug for Randall and the team, we really need something like Arcus to come along for the less than 1 kV. Now, I'm going to give some examples that are going to kind of concentrate on the half keV to 2 kV area, where we are really, we have information from Chandra and XMM RGS, and we really are kind of pushing things at this point. And the two examples I would like to talk about, and some of the thoughts about how we go about working with these poor statistics but high resolution and difficult models. One is the search for signatures of the warm hot intergalactic medium, otherwise known as the WHIM. The other is the search for ultra-fast outflows or UFOs in active galactic nuclei. Now, the main point I want to bring for this discussion of the WHIM is I think we need to be much more careful with statistics when discussing that. We have to think a lot about systematics, and this is going to be a general bit of advice, is we need to simulate, simulate, and simulate some more to really understand have we ever detected something in this particular case. And I think my general conclusion for the WHIM, um, it really is a project for the future. This really was one of the major motivations of Arcus, and I think that is something that still exists. That we need something like Arcus going forward to do some real work in the WHIM. Now, with ultra fast outflows, I think we really do have good examples of these being real. But the goal here is to try to go from blind line searches in the data to physical models. And I think the upshot of what I'm going to say today is that I think we need to think more about the statistics of how we're doing this. Uh, Again, the models are very slow. Uh, we need to develop techniques where parallelization is easy and done with this. We need to think of ways of making this analysis faster and a bit more robust. Markov chain Monte Carlo is very helpful in looking at systems like this. But along those lines, I think we need to open up the models to get at some of the pieces of this to derive ancillary quantities that will be of interest to us. Now, I think we heard some similar thoughts from Anna or Gosevec the other day for a high signal to noise case of NGC 4051. She wasn't specifically talking about UFOs, but I think she was making some of these points that these models are complex. There's a lot of parameter space exploration. Things like Markov chain Monte Carlo are important, and these are things we have to think about. So let me start off with discussing the WHIM. I'm going to give two examples of recent WHIM searches. One is of PG 1116+125, the paper by Bonamente from 2016. And the discussion there I'd like to focus on is how solid was the initial claim, and what did we really need to do to follow up and confirm that detection if it indeed was real. The next object I'd like to talk about is more recent analysis by Kovacs et al. 2019, that was last December, H1821+643. Again, I'm trying to address the question, how solid was the initial claim? And in this case, I think the question is, how much do we have to obsess over the systematics of the detector when we're in this low signal to noise regime? So starting off with the first one, PG 1116+215, this is from the Bonamente paper. This is the Chandra low energy transmission gratings, LETG, used with the HRC detector. This is the minus first order. The thing to note about LETG when used with the HRC is that the HRC does not have any intrinsic energy resolution to speak of, so the various different orders of the dispersed grating spectrum all land on top of each other, and you really cannot do a separation of the gratings orders based upon energy detection in the detector itself. So really what you have, even though this says this is minus first order, in the plot, you really have -1, -2, -3, etc., landing on top of each other, convolved with that spectrum, making the analysis somewhat more difficult. But here in the paper, they really only discuss the minus first order. And you can see there is a continuum, and there are green arrows pointed and red arrows pointed. I'll discuss those in a second. This is the minus first order. Here is the plus first order. You can sort of see that there is a similar continuum, similar features in both, and one feature in particular identified with oxygen 8K alpha near one of the green lines there. Now, all the arrows you see in that particular plot are expected locations of possible O7 and O8 systems based upon HST cosmic origin spectrograph, HST COS measurements of oxygen 6 of nearby galaxies that their impact parameter might then overlap with the line of sight to the AGN in this particular case, and therefore you might expect to see absorption. So this line here by the green near 20.7 angstroms claimed to be an O8 K alpha system associated with the AGN, and that residual was claimed to be 5.2 sigma. Now, the fitted wavelength had to be shifted by about 0.03 angstroms to agree with that expectation from the HST COS spectra. So that right there tells you systematics are important and something to worry about. Now, there can be some systematic issues in the low energy transmission grating wavelength scale that is kind of pushing towards the edge of what you might expect, but it's possible so that the claimant that might be consistent with the expected system at face value could be plausible, but it does show you right away that you start immediately have to thinking about the systematics of the system, not just the statistics of the system. Along those lines within this analysis, as I mentioned before, LHG analysis must include the higher orders. It was not clear from the original paper whether that was true. When you're looking in this low counts regime, very often one uses cache statistics. When one does cache statistics, the background really should be modeled and not taken as measured. And then there's some methodological issues about how does one extrapolate your error bars to the zero bound being no line there in this particular case. From the original paper, the plus and minus error bars were averaged together, and I think that actually gives a misleading significance to the line. I'll mention it in a second. So Jürgen Wilms and I actually took that data and reanalyzed it. This is something that we have not actually published, but we do have all the work on it if anyone cares to see the more details. And here I have shown the spectrum, as before, the LATG as counts per bin, and I have included all the separate orders. So the red lines at the bottom are the second and third order in LATG that needs to be modeled at the same time. The next line is the first order, then the final line is everything summed together. And to figure out the statistics on this is, you had something on the order of 7 different systems with 2 possible lines in each. What was the likelihood that you were going to actually find any random fluctuation with in a reasonable distance of one of those lines? And so this is the point where we have to really start simulate, as I said. So we did 1.5 million simulations without the line and looked for basically noise fluctuations with comparable equivalent with line found at a given distance from a known source, folding in the systematic errors. And doing that just really drops the significance from what's a 5.2 sigma significance down to only a 99.4 or 99.7% significance at that point. And that you have to start really worrying about whether that is a real effect or not. And I should say, actually, when you do the proper cache statistics and you take the asymmetric error bar, the 5.2 sigma really is something more on the order of only 3.5 sigma to begin with. But the bigger effect is the fact that there's a lot of possible systematic lines there that you're looking for, and you're going in and a posteriori kind of picking one of those. And so there's that worry right there that you're not particularly significant. Furthermore, there was XMM data, and this is actually mentioned in the original Von Mente paper, that the line is near but not actually fully in the RGS spectrum, in a gap in the RGS spectrum. That makes it a tricky analysis, but makes it doable. It's still doable. And the line is not fully really in the gap and really should have been seen in the XMM RGS if one actually did the analysis carefully. So you then wonder, is the original line really a systematic issue in LHG, or is it just purely a random chance? Or you have to hypothesize, if it was real in LHG, then there is some systematic issue in RGS that prevented you from seeing it. So both at the same time, again, makes you question whether it should be real. But let's ignore the RGS, pretend that the line was real. How would we go about verifying something like this? Again, what we would normally do when going back to Chandra and say, please, can I have some more time? Very often what someone does is you take your best fit from the original analysis, you take that best fit and redo it with a fake it in XSpec, and then you increase the time and say, okay, what was the statistical significance of that fake it in XSpec? I think for cases like this, we really have to go a little bit deeper than that. And again, going back to Anna's poster the other day, MCMC analyses are very useful in this particular case. So we can take what we saw, model it with cache statistics properly, do a full-blown MCMC analysis, and derive the posterior distribution of the line properties. And that is what is shown on the right here. So the line really could be anything from somewhat much stronger to actually significantly weaker. And then when we go back, we should take draws from this posterior distribution, fake those draws a number of times, and then do the full-blown error analysis on each individual draw. So the question is, what does 280 kiloseconds then buy you? 280 kiloseconds being what was asked for as the follow-up observation to verify whether this was true or not. So drawing 1,000 times on that, doing 1,000 simulations from the posterior distribution, doing the simulations at each, combining it with the original data, and then doing a full fit and error bar search on each of those thousands. These are the results you get for the resulting equivalent width of the combined data and the signal to noise for the asymmetric error bar versus that equivalent width. I have noted here that I do have signal to noise labeled as negative, just because I'm using a convention where if the equivalent width is negative, I make the signal to noise negative. If the equivalent width is positive, I make the signal to noise positive. This way I can just have signal to noise versus equivalent with error bars that smoothly go through zero. Because they possibly could have. Now, doing that fully properly, you find that asking for the nearly 300,000 seconds gave you less than a 50% chance of actually improving the signal to noise to better than 5, which is what I would consider a worthwhile goal to shoot for. That already we see that we if you really believe that this was a true line, ignoring the RGS data, it was an under ask, and you were 50% likely to fail to begin with. And even in the case that doing this, there was a 3% chance alone that the further observations were actually going to decrease the signal to noise in the combined data. Now, jumping to the next example of H1821, similar concept here, looking for the WHIM, but in this particular case, it was one observation where there were 17 sight lines with galaxies with known redshifts and impact parameters. So the data was folded on top of itself to find a feature, and that feature was at 3.3 sigma based upon that. Again, in this case, a Monte Carlo analysis was performed to assess the significance by summing 17 random sight lines and doing draws on that, and it was found to be consistent with a 3.3 sigma. However, this is another one done a reanalysis on. I have stacked the data possibly differently. It's a little hard to read the original paper and know exactly how the stacking was done. I can talk about that a bit offline where I think the differences might be. I got close to 3.3 sigma, but really found it only as a 2.6 sigma effect. So the top one is a flux-corrected spectrum. The spectrum below that is counts per bin, showing with and without the line. And what you see there right next to the putative line is a detector feature. So in this particular case, if we go back and do the simulations, I would say not to choose a random set of 17 lines to do the simulation, but because we are so near a significant detector feature, I would replicate the exact procedure to doing the analysis just to see what that detector feature is possibly doing to you. Now, for both these cases, talking about doing the simulations for the WHIM, you'll notice that there's a lot of me putting in, even though I had programs that were very well defined, did something very well defined, I made some decisions along the way about what to consider significant, how to do the simulations. And that's a general question we have to grapple with how do we account for the usually uncounted human decisions that went into creating the analysis procedure before it became something systematic. Now, jumping to the next part for line searches, again, the message here is that as high-energy astrophysicists, we are slightly insane. We tend to fit continua over 2 to 3 orders of magnitude in energy. I don't know of any other field that does that. We then apply in a lot of these models anywhere from 1 to 6 or so groups of lines, families of lines of different absorbers with different ionization parameters. And even then, we have 3 to 4 orders of magnitude in ionization parameter for a lot of these fits. And the absorbers themselves can be shifted, red shifted or blue shifted by plus or minus 30% the speed of light.
Mike,
That's a hard problem to
right at
solve.
5 minutes left.
How much of it? 5 minutes? Good.
Yeah.
Okay. So I'm going to give some examples here of looking at blind line searches visually using TGCAT, a couple of those, and then talking a bit about a blind line search and another case. And then there's the thoughts on future extensions for line searches. Now, the first place you can go to make this simple for yourself is TGCAT, the Transmissions Gratings Catalog. It's been mentioned in Slack a lot, and there's the location given there. The nice thing about that is you can jump to a spectrum, bin it up any way you want, and see if it's worth your time going after. Here's a case of NGC 3783. Taking all the data in TGCAT and summing it up for a bit more than 1 million seconds, and clearly it's got a lot of lines, as prior analyses have shown. Here's 3 different absorbers in the system. I think nowadays people model it with up to something like 6 or 8 different sets of absorbers. Too complicated for my taste. Here's another example from TGCAT, M81 star. Again, we can play with binning it up. And the nice thing about TGCAT is that you can also go and just set up the line labels. And here's various common hydrogen-like and helium-like lines, and you can clearly see that there's something there worth going after at this point. Now, I show M81 star because this is the first place where we did some blind line searches. The early days of trying to figure out how to do this was by Andy Young and Julia Lee, applied to things like M81 star. And this is something that Jörn and I are working on trying to improve, something that wants to live in the world between doing a continuum plus 1 line at a time, or applying many different worms and ABS models to the continuum and waiting, growing old, and dying as they try to fit. So the concept behind the code is we start off with continuum and add lines 1 or several at a time and kind of run through the whole range of possibilities in a parallelized fashion, keeping the statistics for as we add the lines and put them in and take them out. And then we can iterate this procedure again in a parallelized fashion. So the prototype scripts for this are sitting at Ramice. You can get them, and there's a lot of customization. We plan on doing this to let people choose between fixed and free components, multiple function ties along the lines. Another thing we need to do is, rather than single line fits, we do families of lines at a time. First time I did this was an optical example. I'll just say this quickly. Optical was easy because all the lines are exactly where you expect them to be. Even though I know nothing about optical spectroscopy, the lines are strong, easy to identify. You can go to Google, you can find them on because they're not shifted by 30% the speed of light. Again, the optical guys don't know how easy they have it. So here's a case of doing this in the X-rays. We're applying that blind line search to PG1211. It's a fairly faint AGN that has claims of up to 6 families of ultrafast outflows. There is the blind line search done to that. And if you look at the strongest one here, there 1 keV in the cosmological frame. What if that were neon 10? And if you identify that as neon 10, then a number of other lines pop up at the same blue shift of 6% the speed of light. And so there's about the order of a dozen lines there that then get nicely identified. And if you fold on that, there you go, it does pop up. So the next steps in trying to make this easier for the community to use is to go from individual line searches to comb searches in redshift families. I think there are some good concepts to steal from the LIGO folks. The LIGO folks do very sophisticated fitting to their waveforms, but they start off with a fairly simple match filter grid search to narrow down their parameter. Can we do something similar? Is it enough to create a simple spline spectrum and then do a match filter on simple grids of ionization parameter versus NH? And then jump to MC-MC analysis with slow detailed models. So we need to then open up those slow models for derived parameters, such derived parameters being things like stability curves. And since WARM-MAPS is slow, the derived parameters should really be calculated at the same time as we're doing the MC-MC, since that's the long pole is the evaluations, the MC-MC. So I'm going to stop at the summary here. High energy, high-res spectroscopy has a nasty combination of needing lots of counts and bins with small detectors, complex models. We're trying to make this a little bit easier on ourselves. We have to be very careful with statistics, simulations, and systematics. I think the WHIM shows that. My own personal opinion is we should not do the WHIM until ARCUS. And then we need to try to make our models more accessible and faster, more open interfaces, parallelization, and finally, we do need CRISM, and if we need CRISM, we need ARCUS. I'll stop there.